Hello, everyone. I'm Paul Drabble, Senior Marketing Manager with Delta Q Technologies, part of the Zappi Group of companies. I'd like to extend a warm welcome to everyone tuning into this session, which is high voltage charging solutions for non-road machinery. In case you don't know, the session is being recorded, so it's available to watch on demand in the future. If you have any questions during the session, please add them to the Q&A tab, which you can find to the top right of your session window, and note that your questions will be sent privately. With that, I would like to introduce my colleague who will introduce the main speaker for the session. Akanksha Kapil is the Content Marketing Manager for Delta Q Technologies and has been driving a series of webinars promoting charging solutions for electric vehicles. Akanksha, I'll let you make the introduction of our speaker and begin the session.
Thank you. And hello, everyone. Good morning, good afternoon, good evening, and welcome to today's presentation on high voltage charging solutions for non-road mobile machinery. If you aren't familiar with our company, we are a leading manufacturer of battery chargers for lead acid and lithium ion batteries and are part of the Zappi Group of companies. As Paul mentioned, my name is Akanksha. I am the Content Marketing Manager at Delta Q, and today's webinar speaker is Murad Cherokee, Senior Product Manager. Murad joined Delta Q in 2016 and has over 25 years of experience in product management across engineering, marketing, business and administration in various industries. At Delta Q, he spearheads new product strategies across power conversion, battery charging, vehicle electrification, and regulatory standards. Just a reminder again, the webinar is recorded. We do highly recommend that you submit your questions to the Q&A tab, which we will address at the live Q&A portion of the session. And you would be able to watch this webinar after this session's over, the recorded version. As you all know, this is the last part of our three-part webinar series. If you don't know what the other series were, Part 1 happened on March 1st, and we have a link to the recorded presentation, which you will be able to access when you get the these presentation slides. In that presentation, we discussed how non-road mobile machinery industry is changing rapidly, moving to battery-powered mobile machinery, and why there is an urgent need for onboard chargers that are rugged, reliable, and fully sealed to stand up to harsh onboard environments. We also introduced our new 3-in-1 XV3300 battery charging system, which was why it was developed and how this charger met the needs of OEMs' voltages, power, durability, and functionality demands. Part 2 happened in April, and it discussed elements on designing compact electric machines for the toughest environments, including the criteria for selecting a robust onboard battery charging system and what to consider when integrating the charger on board the machine. Today's session, which is the last session of this series, will focus on high voltage charging solutions for non-road mobile machinery and what the benefits and challenges are with high voltages. I would like to now pass it on to Murad to begin the presentation.
Thank you, Akanksha, for the introduction. Good morning, good afternoon, everyone. In today's webinar, we will be looking at the standard power voltages levels and how they are changing as electrification expands to different machinery categories. We'll explore the benefit and limits of low and intermediate voltage powertrains. We look into charging methods of high voltage batteries, and we will explore the benefit and challenges of high voltage powertrains. And we'll end up the presentation with a summary slide of the key takeaways, and then we will have a live Q&A sessions at the end. Before we dive into the presentation, let's examine some of the trends in construction machinery electrification. Last year at the BOMA, the largest construction equipment show in the world, held in Munich, there were a record number of electric vehicles showcased. Indeed, more than 60 fully electric battery-powered mobile construction machines were exhibited by 28 major OEMs. Some of these machines were early prototype, but many were in full serial production. The machines varied in size and functions and included excavators, backhoe excavators, loaders, dampers, telehandlers, tandem rollers, paver, and even crawler carriers. The analysis of the powertrain voltages selected by the various OEMs is revealing of future trends in this industry. About half of the machine exhibited were outfitted with 48 volt nominal voltages. There were some other machines with working voltages from 80 to 120 volts, 5 of them. And about a quarter of the machine exhibited have 400 volt powertrains. Then there were 8 machines with voltages with what we call higher voltages from 600 to 800 volt. This is just a reminder that there are some standard voltages when it comes to electrification. And these voltages fall into 5 categories. What's known as the low voltages, those are voltages below 60 volts. Typically, it's a 48 volt nominal. Then there are what we call intermediate voltages. This includes 72, 80, and 96 volt nominal. Then medium voltages for 300 to 450 volts. And then there is high voltages where the voltages extend from 500 to 850 volts, and then there is the higher voltages that is typically above 1,000 volts. So these names are proper to this presentation. They are not. There is no standardization in the industry on any particular name, but for the sake of this presentation, we will use these names to distinguish between the different voltage levels. So let's examine some of the features and characteristics of the low and intermediate voltages. The majority of electrification of machines is happening with this voltage, and there are 2 categories. There is the standardized low voltage category below 60 volts, which inherently is called and considered to be touch safe. This type of voltages allow simple designs and cost-effective solutions. It is suitable for what we call subcompact vehicles. Those are vehicles with nominal powers up to 25 kilowatts. These vehicles also have the advantage of being able to be maintained and repaired in regular service shops. Then there is another category still considered to be low voltage with voltages from 72 to 96 volt nominals. This type of these voltages have been used for decades in various industrial and light mobility applications. These voltage ranges are ideal for compact to mid-size vehicles with nominal power expanding from 20 to 75 kilowatts. The advantage of these voltages is that it avoids the component costs and design complexities associated with higher voltages, namely 400 volts. And there is quite a variety of components sold by many OEMs in the industry for commercial off-the-shelf components and systems. These low and intermediate voltages allows for achieving effective machine performance in the subcompact and compact equipment. They present a simple and shorter development design cycle. The components are widely available from several vendors. And in general, and that's actually the biggest advantage, the total production cost of the machines is relatively lower, and from depending on the application, it goes from 5 to 10% and even more less expensive than similar vehicle built with a 400 volt power system. When you consider that there is lower cost due in repair and maintenance. The total cost of ownership of these machines is even lower compared to higher voltages. These low and intermediate voltages from 48 to 96 volts are very mature and will support machine electrifications towards completely phasing out internal combustion engines in high power subcompact and compact mobile machinery by the end of this decade. Delta Q, a leading provider of charging solutions, offer an extensive portfolio and product range of charging solutions for low and intermediate voltage batteries. The charging power scales from as low as 350 volts all the way to 10 kilowatts, from 350 watts to 10 kilowatts. And the battery charging voltages range from 24 to 96 volts, which are relatively considered as safe working voltages. Recently, Delta Q announced the start of full-scale production of the much anticipated XV5300, the 3-in-1 charging system. This innovative and industry-leading charging solution combines a 3.3 kilowatt AC to DC battery charger that is stackable up to 10 kilowatt if you parallel multiple units. The nominal voltages are in the 48, 80, or 96 volt. The system integrates inside a 500 watt DC-DC converter to power either 12 or 24 volt auxiliary power to different loads on the vehicle. Additionally, the system is fully compatible with EV charging stations either in Europe or North America. The system is very compact in size, and it is available in fan and liquid-cooled variants. The enclosure is made of die-cast housing and is IP67 full dust and waterproof sealed. The charger has a high reliability and is designed for with testing for an 8-year service life. And the system supports a wide AC input range as well as has global approvals. Several safety mechanisms are implemented as well as AMI and EMC filters. When it comes to mid to large size machinery electrifications, the requirement for charging becomes even higher. The vehicle power in these systems increases to ranges from 50 to 400 kilowatts. The battery sizes are typically 60 to 400 kilowatt hours. And there is a need at this power level to actually, and for this application, to support opportunity charging, which is actually typically charging within less than 1 hour, which means fast charging rates from 50 to 350 kilowatts. System also is need to have very high power efficiency. This graph shows the expected vehicle battery charging times expressed in hour on the y-axis here, the vertical axis, as a function of the power of the charger power on the x-axis, and the size of the battery, which is actually represented on the z-axis. Subcompact and compact equipment battery sizes are typically below 60 kilowatt in this range here in the front. This could be efficiently charged with standard AC charging solutions, enabling in many scenarios even to have fast or opportunity charging. Fast and opportunity charging typically provide charging from state of charge 10 to 80% and within 1 hour, and in as little as maybe 20 minutes. For larger and heavier equipment, the battery sizes grow beyond 100 kilowatt hour, and this is what's represented in yellow and blue in the back of this graph. The sizes can go up to 400 kilowatt hours. At these sizes, AC charging enables overnight charging, but is not able to support opportunity charging. Therefore, there is a need for shifting to DC fast charging for rates up to 350 kilowatts. So the low and intermediate voltages below 120 volts, have some limitations when it comes to actually large machines. The AVSE, the charging station, DC fast charging is not available and not supported at low voltage levels. AVSEs typically have a minimum DC charging of 200 volts, and therefore at 60, at 48 or 90 or even 120 volts, no AV charging station will be able to charge those batteries. The current typically needed for large equipment actually goes above the 500 amps, which is actually not practical, which makes actually making conductors not practical as the sizes get very big. Battery cooling becomes also a challenge at these low voltage levels, and there is high heat dissipation in the system. So that's actually what drives the need for larger size equipment to high voltage powertrains. Still, 48 volt low voltage and 120 volt voltages architectures will continue to be the solution of choice for high power, subcompact and compact mobile machinery, as well as light mobility electrification. So let's look now at the high voltage powertrains. This table here summarizes a comparison between the different voltages expanding from below 60 volt, the low voltages, all the way to the high voltages above 1000 volts. And you can see in the first row here, the typical vehicle nominal power that ranges from below 25 kilowatts all the way to 600 kilowatts. The main feature, actually, the differentiate between the different systems is the level of safety protection that's available. For example, at the low power level, there is no much protection necessary because the voltage are deemed touch safe. However, when you go into the 400 or 800 volt systems, then there is needed such as actually reinforced or double protection, and even insulation monitoring, current limiting, etc. Technologies are evolving in this semiconductor, but the remains actually the main attractions for the lower voltages is actually the low cost, and for the voltages below 60 volt is the ability to repair and maintain the vehicles in regular service shops. Higher voltages require specialized training for people doing the maintenance and the work on the machine, and special equipment similar to what's happening in EV in electric vehicle workshops. The main attraction actually of the 400 volt systems is the ability to actually do DC fast charging, and indeed actually fast charging rates are supported up to 150 kilowatt. It is important to note here that any charging rate above 50 kilowatts require the supply cables from the charging station to the vehicle to be liquid cooled. And that's where actually the attractions of 800 volt systems, where such cooling is not needed, up to 250 kilowatt providing really fast chargings up to 350 kilowatts. There are in the industry, it's still in its infancy, emerging technologies, powertrain systems that will be operating above 1,000 kilowatt, typically around 1200 volt levels. These are geared towards supporting ultra-fast charging at megawatt levels. And there are talk in the industry about up to 3.75 megawatt charging. For mid and large size industrial machinery, the most reliable and safe solution for charging is using standard EV charging stations. What's known as Mode 1 and Mode 2, enabling charging up to 7 kilowatts, are not very applicable to this system because either they are lacking the safety mechanism or not providing the high power necessary for the applications. What is being used and suitable for these applications is Mode 3 and Mode 3, which is actually AC charging, and Mode 4, which is fast DC charging. As for connectors and plug and connectors, there are several standards depending on the region. So we can so there is in North America there is G1772, also known as Type 1 connectors to support AC charging. In Europe there is Type 2 IAC Type 2 connectors, and GPT in China. For DC charging, it's similar, but it's actually achieved with what's called combo chargers, which combine AC and DC plugs. So in North America, there is a combo plug called CCS1, and in Europe, typically there is CCS2, and in China, GPT standard. For this heavier equipment, the high voltage onboard charger requirements to charge battery sizes from 30 to 400 kilowatts. The charging time spent from as little as 10 or 20 minutes up to 10 hours for overnight charging. The charger needs to support high power AC charging with rates from 7 to 44 kilowatts, and that could be either single phase or three phase. The system also needs to support fast DC charging with rates from 50 to 300 kilowatts. The battery voltages range from 300 to 900 volts, and in this there are 2 or 3 ranges. So like the simplest one is what's called the 400 volt range, which ranges from 200 to 450 volts, and then another range from 500 to 900 volts, and sometimes it's divided into two categories, 500 to 800, and then 800 to 900. Continuing on the requirement of an onboard charger for this high power heavy machinery, there is a need for the charger, the onboard charger, to be very compact and small in dimension. It needs to be liquid cooled and offer ingress protection at the level of IP6K 9K, which actually is water and dust proof, but also is protected against a high temperature, high water jet. The vibration and shock are very, very important, and the charger and the systems need to comply with very high level of unsprung masses. The chargers need to have the regulatory approval required for different regions, as well as they need to have EMC protection and EMI filters. The systems on these machines are expected to have a very high reliability and be designed with a 10-year or more service life, as well as the components, including the charger, need to support PIP-up quality levels of 1 to 3 quality levels. Until recently, 400 volts architectures have been the norm in automotive electric vehicles. This powertrains, indeed, they have lower cost and design complexity compared, of course, to higher voltages, such as 800 volts. They use standardized EV electric vehicle automotive powertrain components. Onboard chargers typically are from 3 to 11 kilowatts, and they support fast charging up to 50 kilowatts, maybe a little bit more with more sophisticated systems. And there is actually quite a significant deployment of EV charging stations to support both AC and DC fast charging. So this voltage level that is predominant in the automotive industry is actually making way and is being adopted for mobile machineries, as we have seen in the stats we provided about the BOMA show. And some OEMs for even larger machines, for heavier equipment, some OEMs are increasing the voltage and shifting to 600 to 700 volt electric systems because of the availability of sub 800 volts peak voltage semiconductors, as well as 600 volt classification for components such as wiring and insulation. However, these 600 volts to 700 volt systems may only be transitory and eventually would fade away within 3 to 5 years to a full transition to 800 volt architectures, where the peak voltages would reach the 900 levels. And that's the solution that provide the best performance. Indeed, 800 volt systems have first significantly reduced charging time. Some of the systems are able to achieve a charging from 10 to 80% of the batteries in less than 20 minutes. That is twice as fast as charging 400 volt batteries, using exactly the same cable, but providing more power. So this means that there is less downtime for operators and less waiting at the fast charging stations. Second, these systems and vehicles use less resources. Indeed, thinner conductors are used, which allows for reduction in vehicle weight and space, and also using less metals and less costs for the conductors. Third, there are improvement of the energy efficiency across the entire vehicle, which means limiting unnecessary power losses. The same charging plugs and charging sockets used for 400 volts can be used without the need to actually use liquid-cooled variants. Better thermal efficiency and heat loss reduction means less weight on the vehicle and higher performance, which translate in either more runtime or smaller batteries being used. All these factors combined lead to a higher sustainability, as well as reduced battery size and lower vehicle weight size, and higher because of this higher efficiency. So these are some of the main drivers for pushing for 800 volt systems. However, the systems have inherently some drawbacks, and the number one obstacle to actually wide deployment of 800 volt systems is the availability of 800 volt DC charging stations. Indeed, if we look, for example, in 2020, the DC charging network deployed worldwide was in excess of 400,000 publicly accessed fast chargers. But very, very few stations are supporting 800 volts. All of them, the maximum voltage is 500 volts. So for only 400 out of 40,000 total charging stations support 800 volts. This is a major impediment for faster expansion of 800 volt architecture in automotive applications that heavily rely on public charging infrastructure. The good news is that recently, most EV charging station manufacturers started future-proofing their DC charging system by increasing the upper limit of the voltages to be compatible with 800 volt systems. Industrial and commercial operators don't typically rely on no-road on public charging stations. They have their own private charging infrastructure, which could use new EV charging stations that support 800 volts. So it won't be very problematic to deploy it for no-road machinery. The use of new generation of semiconductor improve efficiency of the electric motor in one hand, but in the other hand, due to very fast switching cycles and rising increases the stress on the components and insulation systems due to electrical arcing, also known as partial discharges, and require more robust fuses, cable insulation, plugs, contactors. All these elements need to be redesigned for newer specifications. There is also an increase of EMC challenges. The system need more complex thermal management, especially inside the battery compartment, inside the batteries themselves. There is an increase on the stress on the component, as well as one of the downside is the unavailability of materials and component and subsystems designed for 800 volt systems. And the last issue is these components, when available, they have a very high entry prices. The 800 volt vehicles have currently have some inherent design challenges that OEMs need to be aware of. So the systems obviously need to have HVIL or high voltage interlock loops, which helps ensure any source of danger are removed by immediately notifying the system and disconnecting the high voltage system. Some systems employ pre-charge systems to prevent large inrush of current from moving through the power system when it's turned on, which could otherwise cause a lot of damage and dangerous situations for those working with the system. There may be also a need for bleed-off resistors that help to safely bleed off after it is disconnected. Due to the high levels of capacitance in high voltage systems, there can be a lot of voltage and power still remaining after disconnection. The high voltages and noisy environment in the drive systems require robust and high-performance galvanic isolation to ensure safe and reliable operation. Often, the creepage distances and insulation resistance need to be doubled compared to 400 volt systems. And in particular, there is a need for developing and producing a class for 800 volt EV cable capable of properly handling voltages up to 1,000 volt peaks. One of the major challenges in the systems lies in continuously monitoring the insulation faults or loss of isolation, then providing early interruption. The causes of such insulation fault is in normal operation can be, for example, due to contamination, salt, humidity, faulty connectors, or mechanical influences. Evaluating the thermal and electrical stress on insulation systems, selecting proper insulation material, assessing the compatibility of the materials, and finally testing and analyzing them under real-world conditions are necessary. Additionally, there are AC and DC leakage. There need to be AC and DC leakage current sensors that are designed to monitor the resistance conductor connections and continuously measuring and analyzing the residual and fault current and providing interruption if there are any faults. Finally, due to the high switching frequencies, elevated voltages, and current switching significantly increases electromagnetic interference on board the systems when high voltage power conversion systems are used. Electromagnetic compatibility, EMC components and filters help maintain the correct operation on onboard of the onboard communication network and all the different equipment that are present in the electromagnetic environment. This includes our presentation, but I would like to quickly summarize the main point or takeaways from this talk. Low voltage or intermediate voltage, 48 to 120 volt powertrain architectures are very mature and will support machine electrifications towards completely phasing out internal combustion engines in high power, subcompact and compact mobile machinery by the end of this decade. 400 volt will continue to be the voltage of choice in the short term for powertrain electrification and mass commercialization of cost-effective, compact to mid-size machinery. For the long term, 800 volt architectures are emerging to provide the ultimate performance for heavy mobile equipment powertrain full electrifications. The development of technologies and components supporting high voltage powertrain architecture is happening rapidly. Vehicle manufacturers looking to electrify heavy machinery powertrains need to consider many aspects related to the system, architecture, design, component selection, safety, regulatory, reliability, and service. And this brings us to the end of this presentation. I would like to thank you for your time and attention. Let's move on to some questions and answers. If anyone has any questions, we'd be happy to address them.
All right, thanks, Murad. Terrific presentation there. We have 7 questions to go through. So the first one is, will the compatibility for the GB/T charging standards, which is the China EV standards, be available in the future for the XV3300?
So this is not considered at this point for the XV3300 at this point, but we are investigating this topic and will evaluate the possibility of doing that.
Okay, here's another question. Are there any industrial charging standards for high voltage?
Well, the standard EV charging stations currently, like what's deployed in most of the world, they support charging voltages up to 500, maybe a little bit above 500. However, I have looked at many of the major EV charging station manufacturers, and most of them, they actually have in the newer version of their stations, they are actually now supporting in excess of 800 volt charging solutions. So they are actually preparing for the shift in the industry, in the automotive industry, which actually will spill over into the non-road machinery for supporting 800 volt systems. Now, there is still in research, it's in infancy. There are also talk about even higher voltage, above 1000 volt, 1200 to 1500 volt powertrain, but that's still relatively new. So we should see it maturing over the next 7 or 8 years.
Okay. The next question, is there a common charging connector that is used for high voltage charging globally? AC and or DC?
Unfortunately, there is no global standard for either AC or DC. It's regional. But what's being common is in Europe there is a standard connector, CCS2, that would offer actually compatibility with AC and DC charging in Europe. CCS1, which is compatible in North America. China, they have their own standards, and we see also Tesla type of connectors and charging stations, especially with Tesla opening their charging stations to everyone. So I won't be surprised. And now actually automotive EV are starting using those charging network, and I won't be surprised actually to see them in the Tesla charger being used for non-road machinery. So unfortunately, there is no universal standard. So there are there is an IEC universal standard, but the implementation depends on the region.
Okay. Will there eventually be a global EV charging standard?
Well, we hope so, but at this point, it's not there yet. It's not there. It's there is still systems per region. Like, so there are 4 or 5 different concurrent solutions, but who knows? But even if there is such a standard, I won't. It probably will take probably 7 to 10 years to actually be adopted worldwide, just because actually there is a wide deployment of EV charging infrastructure currently all over the world.
Okay, next question. Do you have charging systems for sodium batteries?
The charging station, like if it behaves like the other batteries, like the current chargers could be able to charge those systems. I'm not particularly familiar with the details of the sodium, but because of the flexibility and the intelligence of modern chargers, I'm pretty sure they will be able to adapt to sodium batteries.
Okay, next question. For long-haul trucks and buses, do you see voltages going above 1200 volts?
Potentially. I think for now, I think what I do see is still sticking with the 1500 volt limit for buses and trucks, because they will be able to achieve the requirements for what's happening. But development will continue. I mean, like there are research like in all phases, but I think in the next decade, I would say 1500 volts would be the limit, because actually there are safety limits. When you go above 1500 volts, the next actually logical and limit is at 5000 volts, which is quite high voltage. So it's being used in certain stationary applications, but for using for mobile applications, there is a lot of standards and research and development and investment that's needed there. So I don't see that happening in the midterm.
Okay. Some great questions here. Next one, can you expand on the differences between these chargers and what's offered in the automotive industry that offer 400 to 800 volts DC onboard chargers?
Okay, so onboard chargers, there is for example, for 400 volts, it's widely used for full electric electric vehicle in the automotive world. So pretty much the majority, or actually I would say 98% of the car brands there that are fully electric employ 400-volt powertrains. 800, there are several OEMs that actually moving some of the models to 800 volts, so it's starting to be deployed and used there. So chargers have been there. However, these chargers that are designed for automotive markets are not very suitable for off-road machinery, for off-road and industrial machinery, and there are several reasons for that. The first one is actually the shock and vibration profile for these different applications is not the same, as well as the temperature ranges that are used and then the condition where it's used. So when you have a charger that is embedded inside an electric vehicle, it's completely protected from outside environment, from water, from dust, from everything. In industrial machinery, that's not the case. It's exposed to a lot of environmental stress. That's one aspect. The second aspect is in automotive today, in automotive markets, the chargers that are developed for those applications are almost in every time they are custom applications. So for example, if manufacturer A, they have an electric car, they contract a specific company to design a custom solution for that particular vehicle. And they ensure there is high volume for that, like with serial production of one type of vehicles. In industrial applications, there is just not the same scale as automotive market. So the supply, even though there are actually chargers, but those chargers are not designed for small to medium serial production. That is the case of industrial applications. So although there are quite a few providers there, they design custom charger for specific applications for very high volume. So there is a gap in the industry currently to the specifications, but as well as the services and adaptability to this new paradigm that is happening with progressive electrification for industrial vehicles.
Okay, final two questions. Do you feel contactless charging has any future?
Contactless, or also known as wireless chargers, has its own place in certain applications. But currently, there is quite a bit of premium with regard to employing such application, like for example for contactless charging. So there is definitely in certain applications, especially if it has to do with high frequency charging, or even maybe continuous charging in certain applications where that technology would be applicable. In the short and medium term, the technology is not mature enough, and the cost premium are not there yet. Additionally, even though it's a contactless charging, the vehicles still have to go to a specific location to actually get chargers, which remove a lot of the attractions of having this wireless charging. But there is certainly certain applications where it will be applicable. I would say it will in heavy machinery, especially outdoor machinery. It will be still a niche application. Application will be conductive charging.
Terrific. Okay, so a final question that we have: are the safety training requirements for 800 volt different from what is needed for 400 volts regarding the assembly and service personnel?
Yes. So there are different levels. It's different levels, like between 400 and 800, because at 400 volt levels, there are standards which allow actually some some of these systems to be exposed if there are certain protection implemented. In the 800 volt levels, there should be no contact with live parts. So yes, the levels are different. How to deal with them is different, and also the hazards are very different. So 400 volts, if the current is interrupted within let's say 20 milliseconds, if there is a device there, then there will be no lethal consequences. With 800 volts, any exposure could be potentially very harmful. So yes, the training, the equipment have to change, moving from 400 to 800 volt levels.
Oh, we have one more question. How do you think off-road equipment will be charged at the job sites in the future, away from any public charging infrastructure?
Yes, good question. I still the heavy equipment. I believe from what I see today. Now I'm talking here the next this decade, like from now until 2030. I do see using private charging stations. So the charging stations, especially are designed for outdoor, and they can be installed on a temporary basis at a construction site. I do see that as the best solution, because this is at this point, this is the safest, to provide the safest and the most reliable and rugged solution that exists today, because it's designed actually to charge in the outdoor. So EV charging stations, especially mobile transportable ones that can be connected by an electrician on the site, and then temporarily installed until finish on the job site, and then it can be taken and moved to another location. So there are solutions that are available today. I think that offers the robustness and the safety necessary for today's job sites. Now there is an additional challenge with job site is actually the availability of power, of AC power in that site, like from the grid or from the utility to actually that job site. So in that, actually the industry is being aware of that, and there are solutions that are being deployed today with the stationary containers of batteries. So it's like a big container that could be from 100 kilowatt hour to 1 megawatt. It's a big container, so that get charged in a certain location and transported to the job site, and then would provide 1 or 2 days of charging for several machines that can go there. And that will be that is a very good solutions in the absence of actually grid power grid availability as at the exact job site. So the industry have been from different partners working together to actually resolve all these implementation issues. So it's paving the way to full electrifications at all category and size levels of the construction equipment.
Okay, that's all the questions that have been submitted. So thank you, Murad, and a heartfelt thanks to everybody who attended this session. We hope it was really informative. And if you have an interest for more sessions, please return to the lobby, and you can select more content that you can jump into. So thanks, everyone. We'll wrap it up, and we'll look forward to seeing you on more broadcasts. Thanks very much.